We are now recording. Slideshow set up. From current slide. All right, last time. First, any questions on anything we've covered so far? And by the way, and you probably won't see many, but in case you do, if you happen to see some folks wandering around campus, look like it might be lost, could use a little help, please always help folks out like that. But we've got supposedly on campus today some students that were students at ITT Technical Tech. Okay, that campus, that college, closed their doors at the beginning of fall term. Unfortunately, their fall term started after ours did. So those students couldn't come and get in ours because we were already started the term. But they can get in second mini-term. We've opened a lot of classes for them. Hopefully they can find enough to do. And we're hosting on this campus students who have inquiries from that. Also, Brown Mackey is in the process of closing. So there may be some of those students as well. And some of the other for-profit schools may be on the verge. So we could have a fair number participating in that. So if you do see the folks today, help them out. This building is hard to find things, so help them find their way around if possible. Okay, any questions? All right, we're in section 12.1, vectors in the plane. Chapter 12 is vector geometry, and we were down to example 2 on page 627. At least that's where my mark is. Is that what y'all have? Okay. Now, why has my screen just disappeared? Let me try another function F10 and see if that will help. Yeah, okay, now we got them both back. I don't know what happened there. Now, example 2, page 627. Pretty straightforward. In fact, this is, hopefully you're finding pretty easy stuff. By the way, the views, this morning when I taught my first calculus class, this thing was scooted that way and this was up here, okay? And everything was off-centered, okay? Now it's back being good, so I'm glad it is. I'm not complaining, but it makes no sense why it should do such things. Okay, here's example 2. Sketch the vector V is 2, and by the way, let me get the vector notation down here. Well, they have it. They almost have it. Let me get, yeah. Now I can hit these. This morning, these were not available. First class they were, second class they weren't. Okay. Here is the vector V we're going to be sketching. Oh, I can see it somewhere here. There it is, okay. V, vector V. Now, I can't write bold, so I always put a vector sign over mine, vector arrow, is equal to 2, negative 3. Okay. Now, I do my angle brackets a little more distinctly than they do, especially on a small thing like this and smudgy and stuff. Hard to see. There's vector V, 2, negative 3. How do we sketch that on Cartesian coordinates? Okay. Let's see, did I read the whole problem here? Oh, wait. Sorry, I didn't read enough. Sketch the vector V, 2, negative 3, based at P, which is, and P is, now what do you notice some difference there between these two statements here?
Well, V's a vector, P's a point.
Yeah, V's a vector, P's a point. What gives it away? Okay, the angle brackets for the vector, a point is parentheses. Also, the labeling, V, I can't write bold, so I put the arrow over it. P doesn't have an arrow over it, so that's a point. Okay? Now, when it says based at, that means the initial point is there. So then this is V based at, or the initial point at 1, 4. So you go right 1, up 4. That's your initial. And then from there you go right 2 and down 3. And that puts you right here. So Q being at 3, 1. Parentheses 3, 1. That's the point again. So there's your vector V, component 2 to the right and 3 down. Okay? So that's the first part. Pretty easy to do, right? And the vector V0, also a vector, equivalent to V placed at the origin. Basically, that is an extremely big piece of cake, okay? In that all you have to do, V0 would then be based at the origin, just go right 2, down 3. Because the Q for it, the terminal point, will be exactly, if it's based at the origin, V0, based at the origin, then its terminal point will have the same coordinates that the vector has components, 2, -3. So there it is. Pretty simple to do. Vector notation, the best way to express vectors in my book. Okay. Any questions on that? All right. Now let's move on to vector algebra. What can we do? What are our normal operations in algebra? Adding, subtracting, multiplying, dividing. Now we're going to add a little. We'll talk about how you do subtraction. We'll do certain types of multiplication. And basically division is the inverse of multiplication, so we maybe do a little bit there. Mostly adding, subtracting to begin with. Okay? And so we'll actually only talk about 2. Vector addition, that will define subtraction in terms of addition, just like we normally do. And scalar multiplication, the only type of vector multiplication we're going to talk about now. So let's talk first about vector addition. The sum of 2 vectors, V plus W. Okay? Now, if they have the same base point, and they don't have to, but if they do, and I'll blow this up for right now. Can I get it all in there? I think I can. All right. This morning that would have been off scale, okay, even though it's all on my screen it wouldn't get. If they have the same base point, which they don't have to have, but if you are talking about this, V added to W, sum of V plus W, take V and then, and this is if you're doing it graphically, take your W and move it off the base point of V and put it at the terminal point of V, okay? But keep it same magnitude and direction, equivalent vector, but just moved up there. And then that's what they're calling W prime. And then once you have that, then your sum vector is going to start at the initial point of V and going to the terminal point of W prime in this case. That's your sum, V plus W. Now, that's one way to do it. Another way that you could do it graphically, and graphically is not the best way to do addition of vectors, but it's the way you can, is complete the parallelogram that you have here. In other words, put W up here just like we did, and put V over here. Okay, we didn't do that, but guess what? If we had done W plus V, W, then we'd move V to here, and you'd have been at the same point. So if you did both of those simultaneously, transport W up there, V over there, then the point where they come together, that would be your terminal point for V plus W. It's called the parallelogram method, which basically I usually consider this parallelogram too, but there you actually draw the parallelogram, V parallel to V and W parallel to W. And here's that picture. Okay. Yeah, I'm talking about vectors. Okay, got it. Okay. So, pretty easy going. Now, is that the best way to add vectors? having to draw pictures.
Sorry.
Okay. There's a much easier way. Say again? You said speak for myself? Huh? Okay. Now, what if you're adding a whole bunch of vectors? You can do it by, it won't be parallelograms anymore. It will be, polygonal, I guess is how you say this. But what if you're adding vectors v1 plus v2 plus v3 plus v4? Here's your v1, there's your v2, there's your v3, and there's your v4, written all in standard position, okay? Okay. Well, start with any one of them, it doesn't matter which. If you started with v1, then add by translating v2, not changing magnitude or direction to the end of v1, then you have it up here. Then take v3 and move it up, again translating, not changing magnitude or direction, and then v4, you'll translate to that, and your sum vector would be somewhere here, and that is it. And that closes up your polygon. Okay, sounds like a weather forecast, doesn't it? Closes up the polygon. But of course, it's not always exactly a pretty polygon like this. If you had done it in different order, like v2 plus v3, v2 plus v3 plus v4 plus v1, you still would have had a closed polygon. But you could have them so they cross there, and it wouldn't actually be a closed polygon. But you get the general idea, and I probably should have blown that up too. Sorry, I forgot to do that. Okay, that's how you add a number of vectors. All right, now, is that the best way? No. Okay, we're going to get to the best way in a minute. Now, vector subtraction is carried out by adding the opposite of one vector to another. And what do we mean by opposite? The negative, exactly. Okay, what do we mean by the negative of the vector? Yeah, okay. Doing component-wise, changing the sign of every component. That certainly is it. If you're doing it graphically, the opposite of V1 would be in the same line of V1, but going in the opposite direction. Same magnitude, opposite direction. Okay, that would be your opposite. So how do we subtract two vectors? V minus W, and they don't show a picture of this one, I don't think. Let me see. Yeah, they do somewhere, but it's, yeah, here we go. They do it. All right. And I can see here, Jonathan, right? Okay. Good. Yeah, pretty good representation of the folks here now. All right. So let's do vector subtraction. What if we're trying to do V minus W? Here's your V, there's your W. Well, V minus W is V plus the negative of W. Well, the negative W, if that's W here, the negative of W is V back here. Exactly the same magnitude, but exactly the opposite direction. Move this up there, and then you have V minus V plus a negative W. This will be V minus W there. Now, some people like to picture that as a sort of a parallelogram thing too, and if you're okay doing it, it's fine. What they tend to do is V, well, let's say it this way. V minus W is equal to some vector, this red vector here. Let's call it R. So if V minus W is equal to R, then then V is equal to R plus W. So R plus W, sure enough, gives you V. So if you started with V and put your W here, but this is your resultant, okay, what I was calling R, now it looks like G, okay, because it's green. G plus W is equal to V. So you form another closed box this case, generally a triangle, okay? Not a box, but a triangle. But I don't recommend you do that. There's a much easier way. I like V plus a negative W. That shows it to me exactly. But more simply, V minus W is the translate, I think it's supposed to be translation of the vector pointing from the tip of W to the tip of V. Now, if you want to remember it that way, fine. I don't choose to do so, but it's up to you. Perfectly fine. Okay? That's not the easiest way to do vector subtraction either. We'll get to that. Okay. Now, somewhere here, they're going to start talking, they mentioned in the text, scalar multiplication. Okay. Let's do a little verbiage first. What do we mean by scalar? It's a number. No direction, nothing, just a number. Basically a magnitude. Okay? Except scalars can be negative, the magnitudes are always positive. So it's not quite the same, but it's so. Term scalar is another word for real number. We often speak of scalar versus vector quantities. Thus, the number 8 is a scalar, while angle bracket 8, 2 is a vector with a horizontal component of 8 and a vertical component of 2. If lambda is a scalar, most books use C as that typical scalar, but this one likes lambda. Lambda is a scalar, V is a non-zero vector, then the scalar multiple, lambda V, is defined as at the bottom of page 627. Lambda V has the length of, or magnitude of, absolute value of lambda, okay, because when we talk about lengths, you're dealing with positive numbers. So lambda could be negative, so do the absolute value of lambda times the magnitude of V, okay? You've scaled it up or scaled it back, depending on the magnitude of lambda, okay? So that's the length. It points in the same direction as V, as long as lambda is positive. If lambda is negative, it points in the opposite direction of V, just like the negative of the vector we were talking about before. Okay? Now, that leads to this expression. Basically, this is the thing I just said, but they said it on the previous page, and now they're saying it on this page in a box, and that the magnitude of a scalar times a vector, okay, lambda V is a scalar, bold V is a vector, is the magnitude of that would be the absolute value of lambda multiplied by the magnitude of V, okay? Because magnitudes are always positive. Lambda doesn't have to be positive, it can be positive or negative, so it would be the magnitude, the absolute value of lambda times the magnitude of the vector V. That would be what the magnitude of lambda V is. All right. Now, I think these are some illustrations of scalar multiplication. But let me see. This seems to be what should come next. Here is vector. Okay, this is a whole bunch of different things. Here is vector V, the red one. Okay, vector V. 2V, or not, okay, is the vector that's twice the length of V, but in the same direction of V, so basically you just double its magnitude. This is V, add another V to it, and that gives you 2V. That's the blue vector, okay? Twice as long, same direction. Negative V would be the same magnitude, but going in exactly the opposite direction, okay? That is negative V, okay? All right. It's Tony, right? Yeah. Had you and then lost you. Okay. And the glare. Okay. All right. Any questions about that? And by the way, we talk about this as the opposite or the negative of V, but it's also the vector V multiplied by the scalar minus 1. Same deal, just another way of saying it. Okay? Just like the opposite of a number is that number multiplied by negative 1. Negative 3 is opposite of 3. 3 is opposite of negative 3. Okay. Now, all right, now let's look at some vector operations. Using components. This is how to go, folks. Okay. Let's say we have two vectors. Here's vector V, bold vector V. I would draw it with an arrow over it. A, B are its components. Those are the angle brackets. Vector W, component CD. Okay? Remember, the first is always horizontal, the second is always vertical. You get more than 2 dimensions, you have to define those two. But we're in 2 dimensions now. Then, for any two vectors, 2-dimensional vectors, V and W, with those components, if you're going to add the two vectors together, add the horizontal components, A plus C, comma, B plus D. That's the way to add vectors. Drawing parallelograms and tip points and those kind of things, piece of vector subtraction, just exactly what you would expect, I hope. First component of W, V minus the first component of C, if it's V minus W, first component of W, which is C, comma, second component of V, B minus second component of W, B minus D, close angle bracket. That's the way to do it, okay? If you're multiplying a vector V by a scalar, you scale both components by that scalar. In other words, lambda times V would be open angle bracket, lambda A, comma, lambda B. Scale up or down, whatever that lambda is, each of the components by that same amount. And then one final thing they sort of throw in here, V plus the 0 vector, and since we're dealing with V in 2 space, in other words, 2 components, 2 dimensions, okay, then this 0 vector has to be a 2-component, 2-dimensional vector as well. What would be its components? 0, 0. Well, V plus the 0 vector is exactly the same as 0 plus the V vector, which is exactly V, because you're adding 0 to A and B. You still get A and B. Now, what they didn't show and should have, and maybe they've already done so, V plus V W is the same as W plus V, right? Addition is commutative. How about V minus W? Yay or nay? No, definitely not. Okay, so vector addition, just like scalar addition is commutative, vector subtraction, just like scalar subtraction, is not commutative. Okay. Now, these are the pictures that show up before that thing in your book. So let's do them now. I think we can get them all on one blown up slide. Okay. What have we got here? This is vectors, operations using components. Okay. Here is vector V, A for the horizontal component, V for the vertical component. Here's vector W, C for the horizontal component, D for the vertical component, which they have put these in, labeled them. If you're adding the two vectors, tip to tail, I don't care. You don't have to do that kind of stuff. Just add the A plus C. Here's A, there's C. Add that. You get the horizontal component of your sum vector. And then for the vertical component, add to V what your D is. And D is this distance here. Add that to V. And that gives you your vertical component. There's your vector right there. A plus comma, B plus B. That's the way to go. Without even drawing the picture. The picture shows you how they get that. All right. Now, how about this one? I can't tell what they've done here. I guess the first is just vector V, which is a different vector V from this one, so forget that. It's AB, here's your A, horizontal component, B, vertical component. Okay, if you're multiplying that by some scalar lambda, remember, lambda can be any integer, any real number, okay? Any real number. Positive real number, negative real number. Fractional real number, multiple, it could be rational, irrational, anything, any real number, okay? The one they've shown here is lambda is some positive number. Now, I don't know which one it is, but whatever it is, you scaled A up by that amount, and you scaled B up by that amount, and that gives you lambda V would be lambda A comma lambda B. Notice it's in the same line as V, and this lambda must have been a positive number greater than 1 because it made the magnitude larger. Okay? If it had been a negative number, no matter what, it would have been going down this direction. Lambda V would have been down here. Okay? If it was less than 1, it would have been shorter than this, greater than 1, longer than that. Okay? Make sense? All right. Scalar multiplication. So I think we're ready for example 3. Frankly, I couldn't care less whether we had the picture or not, I think. Maybe it'll be helpful later. Let's do it. For vector V, okay, I can't write bold, so I'll write it that way. Components 1, 4, and vector W, components 3, 2. We're asked to do several things. First, calculate V plus W. Pretty simple. What would that be? 4, 6. Everybody see that? It's just so easy to do it in components. The B part is come up with what 5V is. What would that be? 520. Perfect. Just a piece of cake. Okay? Now. And they illustrated here the sum that we did, 4, 6. Here, vector V, 1, 4. Add to that 3, 2. You can either put it up here or whatever. Shoot. So it's much easier to do 1 plus 3 is 4. 4 plus 2 is 6. Okay? So you added the 3 to the 1, you got 4. And you added 2 to the 4, and you got 6. That's the way you go. Who wants to mess with pictures? Okay. Next. Basic properties of vector algebra. Okay? Seems like we talked about some of these, but we haven't formally listed them. What's that? Yeah. So, basic properties of vector algebra. Remember, in vector algebra, we just talked about vector addition, scalar multiplication. Okay? You define vector subtraction in terms of vector addition, so don't make up anything new for that. And we're not messing with division yet. So for all vectors U, V, and W, now these have to be the same dimension vectors. 2-dimensional, 3-dimensional, 16-dimensional, whatever. Have to be the same. And for all scalars, lambda, any real number, we're not doing complex numbers with them. Leave that alone. Then the commutative law is, for any 2 vectors of same dimensions, V plus W is the same as W plus V. Think about adding by components. AB plus CD is A plus Numbers are commutative. The components of your vector, they're commutative too. Associative law, just as you would expect, u added to u plus the v plus w is the same as u added to v and then adding w. Okay? And again, if you do it by components, then you see it has to be true because the components are real numbers. Real numbers are associative in addition. Okay? And that's all you're doing is adding those components. Distributive law for scalars. Okay? I can remember, what is it? The linear algebra book or one of them. They don't put the for scalars in. They just say it's a distributive law. I like that this one does for scalars. Yeah. Lambda times the sum of v plus w. For a scalar outside a vector sum, you can distribute the scalar within. That's the same as lambda v plus lambda w. Okay? Now, if you wanted to prove this, again, do it by components. If this is AB, this is CD, the A plus B, comma, C plus, no, A plus C, comma, B plus D, lambda times that would be lambda A plus lambda. You know, distributes across both of them, you know, that's exactly what you get when you get this as well. So, hopefully those are pretty set. Now, leave that alone at that. Any questions? All right. They talk about verifying these using components, which is what I just mentioned. I'll let you read through that if you want to see any more. There is a term there that they sort of throw out there. Oh, I'm sorry. I was thinking. Here's something else. Linear combination of two vectors, v and w. Okay? And that, I think, is what this is illustrating. I believe it is. We'll introduce that term I was talking about also. Okay. A linear combination of vectors v and w is also a vector. And what it is this, okay? Is some r times v plus some s times w. V and w being vectors, r and s are scalars. They don't have to be the same scalars as any old scalars. Positive, negative, fraction, decimal, rational, irrational, it doesn't matter, okay? Then the linear combination of those, linear combination being combining your vector addition with your scalar multiplication, that makes a linear combination. Then the vector that's produced by that we'll call u, okay? Now, they chose this blue to be vector v and that blue here from the origin up to there to be your vector w. Okay? Now, this illustration is showing that r happens to be a negative number, and it's a negative number less than 1. Or, it's not said well. Negative number greater than negative 1. Okay? Okay. In other words, the absolute value of it is less than 1. Let's put it that way. Okay. So,
between -1 and 0?
Yeah, between -1 and 0. Okay? So, if this is v, you're adding a negative to it, so it'll go in the opposite direction, but it's a scalar whose magnitude is between 0 and 1, so that's going to make this shorter. Okay, so there's RV. Add to that SW. Now, S in this case is also less than 1. Okay, but it's a positive number less than 1. I know that because SW is shorter than W. So that, again, is a scalar less than 1. It doesn't have to be, but in this case it is. Then the linear combination of those two, RV plus SW, is then going to be this pink vector here. Okay. Now, that's all we're talking about here. a linear combination of two vectors. This next picture is illustrating something else, okay? This is also illustrating, the same two vectors, v and w, that we had before, but this time they're letting r be a positive number, but again between 0 and 1, and s being a positive number between 0 and 1. Okay? So RV would be here, SW would be here, and the RV plus SW, R is less than 1 and S is less than 1, then it's going to be completely contained within the space of, you might say, V plus W. Okay? The parallelogram P, that's which one is it? P, the whole big parallelogram, the blue parallelogram here, we say is spanned by V and W, consists of all the linear combinations RV plus SW with R and S being between 0 and 1. So in other words, every vector that you can have a linear combination of those two vectors, as long as you keep your R and S's between 0 and 1, they will fall somewhere inside that space that's spanned by V and W. The space spanned by V and W are the area in between those two vectors and their sum, formed by that parallelogram. That's what that means now. Why are they introducing this? I can't say for sure. I'm not sure we're going to use this. Linear algebra, use spanning, we'll be doing that later, all the time, but I wasn't aware we were going to talk about it here, but that's what it means. So let's do some linear combinations in example 4. I'll blow it up for now, but as soon as I go to write, it's going to shrink back. Express the vector u, which is 4, 4, there it is, in this figure as a linear combination of v, which is 6, 2, and w, which is 2, 4. Okay? Now, they happen to be doing everything just like they did before, but realize this, you don't have to have these scalars be between 0 and 1. This example, just like the earlier one, has it that way. They don't have to be. This one is, okay? But that's not a requirement. What do we mean? Express a vector u as a linear combination of v and w, okay? Well, we know that, let's just write out what linear combination, how to do this. Okay, linear combination, u is equal to RV, RV plus SW. Okay. Now, you know that's what it means to be a linear combination. Well, we know what U is. They gave us that. 4, 4 is equal to R times that vector V, which we used before, 6, 2, plus S times the vector 2, 4, because that's what W was, 2, 4. Okay? When it says express U as a linear combination of R, V, and W, they gave you U, they gave you V, they gave you W. basically what they're asking for you to find the scalars, R and S. So how would we go about doing that? Any ideas? Second?
Distribute the R and the S out, I guess.
Okay, well, what you do is write down two equations, scalar equations, using the components of these vectors. That first component, 4, is equal to R times the first component here, 6, plus S times the first component there, 2S. There's an equation, right? Do the same thing for the second component. 4 is equal to what? 2R plus 4S. Has to be plus, okay? Now, how can you simplify both of those equations? Divide out 2's from both of them. So that system of equations you could write as, this is so frustrating, this thinking thing just collapses on me. Well, okay. All right. I'm going to flip things around a little bit too. I like to have the variables in front. Dividing by 2, we have 3R plus S is equal to 2. Second equation, very similar. What do we have? R plus 2S is equal to 2. Okay. Now, for some reason, my plus up above looks really bizarre, okay? That is a plus, I guess the board moved, okay. Okay, what did you suggest doing? You could do that, in other words, solve by substitution. Yeah, you certainly could do that. Anyone have any other ideas you'd rather do, or you like that? Frankly, it's fine to do that. I just prefer elimination by addition. And it doesn't really matter, but how I would do is pick the smallest numbers. The S's have the smallest coefficients. So let's multiply that first equation by -2. And what does that give you? -6R minus 2S equal -4. And now what? Add those two together and you get and that gives you -2 over -5, which is positive 2/5. Very good. Now, that gives you your R. What would be your S? Yeah, you could plug it in, and doesn't matter where you plug it in. I like that second equation a little bit better because the numbers are smaller. So let's say 2/5 plus 2S is equal to 2. You know what I'd be tempted to do first? Yeah, but actually, I'm going to multiply by 5/2. The reason I want to multiply by 1/2, get rid of those 2's because they're in every term. But let's also multiply by 5. So I'm going to multiply, in this case, and this is almost a special case, by 5/2. Normally, I wouldn't do this, but just to get rid of the 2's. See, each term has a 2 in it. So get rid of that, and this one goes away. So you have 1 plus, I can't read, 5S equal 5. Yeah, subtract 1 from both sides, and you get 5S is equal to 4, S is equal to 4/5. Okay. Now again, there's nothing that guarantees that R and S need to be less than 1 or even between 0 and 1. They could be negative, they could be bigger, they could be, any sorts of things. They just happen to have given you some that do span, or span by that. And that's exactly what they got to. R is equal to 2/5 and S is equal to 4/5, just like we did. Okay? Now, I was just trying to see, I don't think there's anything else that's really super important there. I was wondering if they were trying to normalize, but that doesn't even do that either, so I'm not even going to bring that up. Forget I said that. Conceptual insight here in general, to write a vector U, U1, U2 as a linear combination of other vectors, V1, V2, and W1, W2, we have to solve a system of two linear equations and two unknowns, R and S. That's exactly what we did. On the other hand, vectors give us a way of visualizing a system of equations geometrically. The solution is represented by a parallelogram, as we saw in, this figure right here, figure 14. This relationship between vectors and systems of linear equations extends to any number of variables and is the starting point for the important subject of linear algebra. Yes. Okay. Now, when I was mentioning normalizing a vector, that means making it shrinking or swelling or enhancing it so that its magnitude is 1, but it hasn't changed its direction. Okay? So a vector of length 1 is called a, what's the card game? You play, but then when you get down to one card, you call out Uno. So it's called a Uno vector, no, a unit vector. Okay, same root. Unit vector. Magnitude 1. Okay? Unit vector. Unit vectors often used to indicate direction when it's not necessarily to specify a length, because the length is always 1, okay? So this just gives you basically your direction. The head of a unit vector, E, and hopefully you're not going to find that strange that they use vector E, okay? Now, I just drew it like that, but I usually don't. If that's a unit vector, I do something a little special to it. Rather than putting an arrow over it, I typically put a caret over it, the mountaintop, I put that over it to reinforce in my mind, this is a unit vector, okay? You don't have to do that, it's just my nomenclature. Now, okay. Of course, the book bolds, and that's perfectly fine. So it says here, the head of a unit vector based at the origin lies on the unit circle. Because guess what's true about everything on the unit circle? Magnitude of 1. Okay? Its radius is 1. Magnitude is 1. So lies on the unit circle and can be given by this E. Then it can also be given as, let's just choose this vector here. It's not 6, 2, but some vector here. And let's just say this was on the unit circle. So this length here is 1. What can you tell me about this length here? Maybe not a whole lot, but in that picture it's certainly less than 1, but this one even more so. You can tell for sure that's less than 1. Okay? So those would be the component of this unit vector E. In fact, we're not even going to call it V anymore. We're going to call it E. Has a magnitude of 1. So probably shouldn't say it that way. Magnitude of 1. Now, I'm going to introduce a trig concept here, a geometry concept. This angle is called theta. How can you express the x component of this vector E, whose angle here is theta? Remember, this is E magnitude 1. How can you express this x component of that vector in terms of theta? It's the cosine of theta. You're absolutely right. Remember, cosine theta never gets outside of plus or minus 1, right? Same with sine. So this will be vector cosine theta. And what would be the y component? Sine theta. You got it. Okay? And guess what? That is a unit vector represented by a unit circle centered at the origin for any angle theta. Theta could have been down here, and in the fourth quadrant, cosine is also positive. Of course it is. The sine is negative, and that would have to be too. Over here, sine would be positive. I'm sorry, yeah, sine, the y is positive, the x would be negative. Okay? Down here, they'd both be negative. Cosine theta and sine theta. So yeah, that is your unit vector in terms of the angle theta. All right. And I guess, okay. I've got some of these slides out of order, but here is another nomenclature that you can use. In fact, is used a lot. If you're looking for the unit vector that's in the same direction as vector v, you're given some v that's not necessarily a unit vector. It could be longer, it could be shorter, it could be anything. But let's just say it's not a unit vector. Okay? And let's also say this, it's not the zero vector. So if vector v is not a zero vector, okay. Anyone see a reason why that would be true? Magnitude would be 0, you can't divide by 0. So we're leaving out the zero vector. Exclude it, not even there, okay? So the unit vector in the direction of vector v would be the vector v divided by its magnitude, okay? Now what would that do for you? The magnitude of the vector v in the numerator the vector v in the numerator divided by the magnitude of the vector v in the denominator, and basically what you've done, you've normalized that, that's what we call it, to a unit vector. In the same direction as v, but with unit magnitude 1. Okay? Now, this should have gone with the previous discussion we had. This is what we mean by a unit vector centered at the origin is always going to be, if you know the angle theta, it's going to be cosine theta and sine theta. Those are the components. Because it really should be, if you did xy's, x is always r cosine theta and y is always r sine theta. But on the unit circle, what's your r? 1. Okay, so it'd be 1 cosine theta, 1 sine theta. Okay. Most of the time, we don't think of cosine theta as having dimension. The dimension comes from the radius, which is 1. So that is okay. All right. I can't think of anything else to do with that. Probably beat it to death. So now, what is this one doing? All right. Is this a problem? Let me see. No. Okay. We can always scale a non-zero vector v, v1, v2, to obtain a unit vector pointing in the same direction. This is illustrating that last formula we had. If here's your vector v, the red arrow there, big red arrow, having components a, b, obviously magnitude greater than 1 because it's circle that would have formed would be much larger than your unit circle. Okay. Now, how do we get the unit vector in that direction? We did it a little bit earlier with the algebraic form. It's this vector divided by what? Magnitude of v. And what would be the magnitude of v if its components are a and b? Oh, when I do this, it's going to shrink. Okay. Whoops. Magnitude. Where did that go? Here we go. Okay. Magnitude of v. Okay. The square root of a squared plus b squared. Okay? So, then the unit vector in the direction of vector v, unit vector e in the direction of v, is the vector v divided by its magnitude. Right? That's what we said before. Okay, well this is a b, that's vector v, divided by the square root of a squared plus b squared. Now, another way you could write that would be vector whose x component is a over the square root of a squared plus b squared, comma, b over the square root of a squared plus b squared. Would you not buy that? That is the unit vector in the direction of v. Okay? How would you check that to make sure it's a unit vector? Square, atom, take the square root. So when you square this, what do you get? Over. And when you square that, you get add them together. A squared plus b squared over a squared plus b squared, which is 1. So sure enough, that is unit vector 1. And it's in the same direction as v. Okay. Now, that's, well, I don't think they have a slide of it, but that line that you see just to the right of this figure 16 basically says that the magnitude of your unit vector in the direction of vector v is equal to the 1 over magnitude of v times vector v. Oops. That's what E is. So then you do the magnitude of that. That gives you magnitude of v over the magnitude of v. And of course that is 1. So the magnitude of a unit vector is 1. We knew that. That was to begin with. There we've just gone around in a circle and gotten back to that. Okay. And then as we've already talked about, defining an angle theta with the positive x-axis, wherever that is on the circle, okay, then another way of expressing is this. Okay. Now this is interesting. This slide doesn't look quite the same as the one you have in the new edition. Okay. It's close but not quite. What they have, and if I go to write on it, it's going to shrink. So let me just do it here. They write this as V1, V2, which is later going to be sort of a standard notation for us there. And that's equal to the magnitude of V, which would be the square root of a squared plus b squared, or square root of v1 squared plus v2 squared, you know, whatever, times this unit vector in the direction. That's basically, remember, unit vector is this vector divided by that, so multiplied by some magnitude. But this unit vector, remember, consider the origin would be cosine theta sine theta. These are all different ways to express that vector v. Okay? Magnitude of v times cosine theta sine theta. Of course, cosine theta sine theta defines where you are on that unit circle. Okay? So wherever that was, whatever theta gives you that value, that's sure enough the truth. Now, it seems like to me we're just beating dead horses here. Let's go on and actually do a problem here. I'm not sure we have, I believe we do. So let's just do example 5, I think. Let me just see, I don't think we have, okay. Find the unit vector in the direction of v. And v is the vector 3, 5. I can't find it. There it is. 3, 5. Okay? How would you find the unit vector in that direction? We call that, this book calls it e sub v. What's going to be the first thing you better do? Find the magnitude of v. Okay? Pretty simple process. So magnitude of v is equal to square root of what? 9 plus 25 is 34. Okay, square root of 34. And then what do we do with it? Okay, so you take v, 3, 5, and divide by the square root of 34. And then if you break that up by components, that would be 3 over root 34, comma, 5 over root 34. Okay? That is the unit vector in the direction of v. Okay? Does that make sense? Now, I like to just check those, and it's pretty easy to do, and make sure the magnitude is 1. That's how we check to make sure it's a unit vector, that its magnitude is 1. Well, square this. 9 over 34. Add those together. Yeah, got it. Done. Success. Okay. And that's typically how you write those two as a vector. Okay. Now let's talk about some very special unit vectors that I hope you all already know and love. All right. Here's some, let me blow this up. Okay. Here's some vector v. Okay? AI plus bj. Now, what in the world is that I and j? Okay, I and j are the unit vectors along your coordinate axes. The unit vector in the x direction is I. Unit vector in the direction of the y vector is the y-axis is j. This is one unit here, but they're perpendicular to each other because they're on the coordinate axes. Okay? Magnitude 1. Okay. Now from this picture, what can you tell me about A and B? They're both positive and greater than 1. Okay, very good. Okay? Because A, I mean, just looking at this, appears to be 2.2 or 2 point something or other like that, whereas B appears to be 1, 2, maybe 3. Okay? Doesn't matter exactly what they are, but they are greater than, they're positive and greater than 1. Okay, so there's another way to express a vector, and really that's in component form as well. It's just a little more writing to do. you're writing its component times the magnitude of the component, okay, meaning absolute value of that, no, not absolute value, the value of that component times the I vector plus the value of the J component, of the Y component, times the J value, okay? My eyes are giving me problems. I don't know if it's a glare or what. Okay. So this is exactly equivalent to saying angle bracket A comma B, close angle bracket. AI plus BJ. If you were in 3 dimensions, then the Z component is K, the unit vector in the Z component. We don't talk about unit vectors, well, we don't have any axes beyond X, Y, and Z. We certainly can theoretically talk about 4, 5, or 10 space, but we just don't have any special names for those. Okay. So, what's that?
So we ran out of letters.
Well, sort of, but actually, what you do then is just use component notation. Angle bracket A, comma B, comma C, comma D, comma D, whatever it is. Close it out whenever you reach to the end. You just don't have enough IJ, K's, LM. I mean, it gets a little nuts after that. So usually these refer to physical space, IJ and K. We only deal with I and J right now. Okay. So you tell me what the vector, to write this vector in component note. Yuck. Let me get rid of that too. Okay, I'll do it this way. Okay. Vector 4 comma negative 2. Write that vector in component notation but using unit vectors. For I minus 2j. Okay. Those are equivalent forms. This is component notation using the angle brackets. That's component notation using the unit vectors. Okay? Make sense? Okay. Now, vector addition is performed by adding I and J components just like it was component, adding them within the angle brackets. Okay. Now here it says, it is often said that the quantities such as force and velocities are vectors because they have both magnitude and direction. But there is more to this statement that meets the eye or the ear, okay? A vector quantity must obey the law of vector addition, okay? And let's see if they have a figure here for it. Okay, by the way, here are those unit vectors. I forgot to show this slide, okay? I is the vector, 1 on the x component, 0 y component, and j is the vector, 0 x component, 1 y component. So certainly they both have magnitude 1, so they are unit vectors. If I were writing this, they'd have hats on them. That is your definition of I and J. I forgot to write it down that way, so there it is. All right, this is the figure they're talking about in that conceptual insight. My head is clogging up. Okay. Now, a vector quantity must obey the law of vector addition. So we say that if we say that force is a vector, we are really claiming that the forces add according to the parallelogram law, which why use that, I don't know. In other words, if forces F1 and F2 act on an object, then the resultant force is the vector form of the object. Sorry. Resultant force is the vector sum of F1 and F2. This is a physical fact that must be verified experimentally. Okay. Well known to scientists and engineers long before the vector concept was introduced formally in the 1800s. Okay, so vectors haven't been around that long. So, frankly, I don't see a big reason for this. Let me go back and blow it up again. Slide. I mean, it wasn't really telling me lots. Of course, I can think of several problems it could pertain to. But let's say an airplane traveling with velocity v1 encounters wind of velocity v2, and then the plane, even though it's going like this, the wind is blowing it like that, so its actual flight path would be like this, okay? Because the wind is pushing it up and a little bit ahead of what just the regular velocity would be. That's what we mean by vector addition. Using all parts, okay. So, example 6. I'll have to do away with this as soon as I explain the problem. So here, find the forces on cables 1 and 2 in this figure. Okay? So here's what the figure is. Obviously, cable 1 is shorter than cable 2. You're hanging a 100 kilogram mass at that point, and it can't be sliding. These are fixed. Both of them are fixed. Fixed length cable 1, cable 2. If they were the same length, they would hang down directly in between. It's not. They're different lengths. Okay? So what they're asking for is the force on cable 1 and the force on cable 2. Okay, how in the world are we going to do that? Okay? Now, in physics we say we would draw a free body diagram, okay? And that's kind of what we're doing here, okay? But the force on cable 1 is exerting on this mass, is a force in that direction. Force cable 2 on this mass is a force in that direction. Okay. Now, if this is angle theta here, then draw you a horizontal line here that also is going to be theta. If that's 30, this is 30. If that's 55, this one's 55. Okay? So that's how they were able to get away with this. Force on cable 2, force on cable 1. Okay? If you remember in geometry, I don't know if y'all took geometry, they call those alternate interior angles. Two parallel lines, the line cuts across that, it forms alternate interior angles. Okay? Also have exterior angles too, but we're not getting into that. Okay. Now, the free body diagram part of this says, what are all the forces acting on this mass here? Well, you got cable 2 pulling that way, cable 1 pulling that way, but you have gravity pulling downward, okay? So that's your third force. Okay, and this is a mass. How is mass related to forces? Same thing? Definitely not. Mass is a scalar quantity, force is a vector quantity. How are they related? Acceleration due to gravity, which is, and this is in kilograms, so we'll be using SI units, 9.8 meters per second squared. And it's downward, so that's where the negative comes from. Doesn't have a horizontal component, only a vertical component. So the force downward would be, FG would be 0,980. 100 times 9.898. Negative because it's down. Okay? F1 and F2 obviously have positive X and positive Y, negative X and positive Y. Okay? So you've drawn those properties. Now, another thing they did here, rather than doing 55 degrees over here, they did what do you call these things? Supplement of 55 would be 125, because they add to 180. Okay, so the supplement of 55 would be 125. Okay, now I think you're ready to plot. Okay, this also gives you two equations. Okay, and you have two unknowns, F1 and F2. Okay. How would you go from there? Now, they haven't quite said this yet, but they sort of have. When they're talking about vector sums, you deal with component at a time. So that's what we do here. Okay? Say again? Start with a 0? FG? Okay. It doesn't matter where you start. Let's write what the components are. What's the net force acting on the block, on the mass? The net force is 0 because it's not moving. It's not accelerating. It's hanging there. It's static. Okay? Net force is 0. Okay? So we'll talk about that, and of course, in order to write, I've got to do this. Let's talk about in the X direction, the I direction. Okay? Three forces acting on it. Okay? F1, F2, and Fg. So what's the X component of F1? Okay? It would be X component of F1. Its magnitude is F1. Its angle is 125. So what would be its magnitude of the X component? I'll draw it in here. That right there. Yeah, no, cotangent. Okay. All right. You're using 55, that would be fine. The negative of that, if you use 125, then all it is F1 times the cosine of 125. Because that's going to take care of your sine. Cosine is negative in the second quadrant. That will take care of it. Okay? Plus, and what's the X component of F2? It's F2 times the cosine of 30 degrees. Okay? And what's the yeah, that's equal to 0 because 1 is positive, 1 is negative, they're going to add the 0. It has no third component. Okay? Now, how about the Y component? Right? Of 125. Or 55, it wouldn't matter which one you did, they're going to be the same here. No. Yeah, Y component, yeah, they would be the same, okay? Plus F2 sine 30 is equal to what? Negative 980. Okay, let's see, let's think about that. No, is 980. Plus a negative 980 equals 0. So let's just move it to the other side. Let's say it's equal to 980. Two equations, two unknowns. I know the coefficients are sort of messy, but you got calculators. You can do this. Okay? And we solve those. And by the way, they call the magnitudes little f 1 and 2. I didn't do that, but you can... and they left the minus 180 on the one side. We moved it to the other. It's okay. We can do it either way. What's cosine of 125? Anyone got that yet? We already said it was negative. Be sure you're in the degree mode. Cosine of 125. Anyone got it? Please say yes, somebody. It is a negative. 0.573, yeah, that's what they got. 73 times, and they're calling this little f1, that's the magnitude. Okay, plus cosine 30, it's more familiar, what's that one? They're calling. Say again? A little louder. Oh, square root of 2 over 2. Yeah, that's 3 over 2. You're absolutely right, but let's give me a decimal number. 0.866. That one should be pretty familiar to you. Times little f2 equal to 0. And this one would be, what's sine of 125? 819. F1 plus, I know that one, don't you? 0.500, I'll put down F2, and they put plus a negative, I'm just putting it equal 980, move it to the other side. Okay, and I know it's messy, but it's doable. You can multiply the top equation by 0.819 and the bottom equation by 0.0573 and come up with new things, and you'll eliminate that, and whatever you have over here, go to town with it. It's basically what this tells you is 0.866. Okay, sorry, times 0.819, okay, times F2, okay, that's that sum, plus, I'm going to do this one, 0. I put a 0 in the wrong way. 573 times 0.500. That would be these two multiplied together. These are those two, and that's equal to 0.573 times 980. Okay. So then we would divide by this sum, okay? It's all doable. I'll let you fiddle with it, see what you get. They actually, it looks like they may have done a substitution rather than elimination by addition. It doesn't really matter. But when you get to the end, they got F1 was 852 newtons. That's this way. And the other was 564 newtons this way. And that kind of makes sense, because this one's supporting more of the weight than that one is. So that's got to be a smaller force. Okay. And that's what we're looking for. Not sure what, the rest of this is just writing that in vector form. Why carry that many decimals around? This is a math book, but we'll let them get by with it. Okay. close this section. How are we doing on time? 6 minutes? I think we can do it. Okay. Oh, and here's, by the way, is the arrows asking you for that. They gave it to you here. Okay. All right. There was for 125, the cosine was negative 5.573, the sine was 0.819. 30 degrees, cosine was 0.866, sine was 0.5. We used them well. Here's the triangle inequality. For any two vectors, V and W, any two vectors, V and W, and this is always true, folks, any two vectors, V and W, let me blow this up. This is important enough to blow up, okay? Well, if I could get the box to quit chittering. Okay, any two vectors, V and W. The magnitude of the sum of those two vectors is always less than, or sometimes occasionally equal to, never greater than, but occasionally equal to, the sum of the magnitudes. So the magnitude of the sum of two vectors is always less than or equal to the sum of the magnitudes of those two vectors. Okay? Only times when it's equal is if one of those is 0, the 0 vector, which we usually exclude, or if one of them is an exact multiple of the other. In other words, they're collinear. But if there's any angle in between, then the sum of the vector's magnitude is going to be less than the sum of the magnitude. It's got to be. Okay? Think of your, I don't like the parallelogram method, but think of it. Okay? Of course, when I go to write, it's going to shrink this. If this is vector V, and this is vector W, and you were to add those two together, this is V plus W. Okay. This is W. Add them together. I didn't mean to. Okay. Then, okay, take a look at this. The only way that this would be equal to that plus that is if V and W were on the same line. Anything else, and it gets shorter. If they were on the same line, then W would be here, then that would be V plus W, V plus W, right? Any angle less than or greater than that, then this is going to be less. So the magnitude of this is always less than or equal to the sum of the magnitudes. Only time if these are collinear, then and in the same direction, then it can be equal, or if one of those is 0, then obviously it's equal. If that was 0, then the magnitude W is magnitude W. If that was 0, the magnitude W. So that's sort of trivial. Okay. So that's your triangle inequality. Do we have time for the preliminary questions? 3 minutes. Let's try the first one. Answer true or false. Every non-zero vector is, here's A, equivalent to a vector based at the origin. True or false? Yes, absolutely. Equivalent to a unit vector based at the origin. Okay? Every non-zero vector is equivalent to a unit vector based at the origin. Equivalent? Huh? Same direction, but equivalent means same direction and same magnitude. Obviously not there. C, parallel to a vector based at the origin. Every non-zero vector is parallel to a vector based at the origin. Yeah, I would say so. If it's here, there's one that the origin based there too, yeah. Okay, is parallel to a unit vector based at the origin. Yes. So that looked like true, false, false, true, false, true, true. Let's see what they did back here. Ooh. 11 what? No, 12-1. 12-1. True, false, true, true. Good. Okay. Do we have time for 2? Okay, let's try it. What is the length of negative 3a? What? Ooh. Okay. What is the length of negative 3a if magnitude of a is 5? What is the length of negative 3a? 15. Perfect. Okay. Everybody see that? 12, 15. Got it. Okay. From our definition. Do we have time for 3? 1 minute. Let's see it. Suppose that V has components 3, 1. So vector V has components 3, 1. How, if at all, do the components change if you translate V horizontally 2 units to the left? How, if at all, do the components change if you translate V horizontally 2 units to the left? What should be your first guess on it? Okay. Let's draw it in. Okay. There is vector V. Translate it. So what, 2 units to the left? Okay. Okay, there you translate it 2 units to the left. Have its components changed? No, a translation does not change anything about the vector except its location. Its components stay the same. Now, if we did shrinking or stretching, yeah, that changes, okay? But translation keeps the vector exactly the same. So I'm guessing we're out of time now. Okay, but before you go, okay, we'll start with question 4 there next time, preliminary question. Do homework exercises 1 or 3, 5 or 7, 9 or 11, any of the odds 13 to 17, any of the odds 19 through 27. I would do multiple of those. Any of the odds 29, or either 29 or 31, 33 or 35, 37 or 39. Any of the odds 41 to 47. Any of the odds 49 to 59, no, I'm sorry, 49, either 40, no, any of the odds 49 to 53, either 55 or 57, do 59, do 61, and do either 63 or 65. Okay? Good deal. And you can look at the others if you'd like. We will wrap up 12-1 next time. Good deal. Any questions? What? No, he's going to leave me those keys. I want that Mercedes. Okay? All right.